So in this video, we are going to take a look at strong and weak acids and bases. And so we need to first refresh your memory about the difference between concentrated and dilute acids and bases and strong and weak acids and bases. So concentration is always referring to the amount of acid or the amount of base that you put in water. So before it dissociates or ionizes, what's the concentration of the whole molecule that you started with? Concentration uses the reference terms concentrated and dilute, not strong and weak. So if you have a lot of molecules that you put in water, it's concentrated, it's not strong. If you have very few molecules that you wound up putting in water, it's dilute, not weak. So you got to make sure that you use your terminology properly. The terms strong and weak refer to the amount of dissociation that that acid or base undergoes once it's in the water. So does it ionize completely? Does it only ionize a little bit? So strong and weak acids are, like I said, are really looking at the dissociation or the ionization of the molecule. So a strong acid is going to dissociate close to 100%, if not 100%. Strong acids we're going to assume is 100% dissociation. So you wind up with none of the whole molecule left. It's a go to completion reaction, and everything in the solution are ions. If you have a weak acid or base, the whole molecule establishes an equilibrium with the ions. So in the end, what you wind up having is some whole molecules and some ions, and so equilibrium is established. And that's true whether or not you have an acid or a base. So strong bases and strong acids dissociate completely. So you can find the concentration of the ions simply by doing a mole ratio. So here's the strong acids and bases that you need to know. You need to memorize these if you have not done so from first year. So there are six strong acids. Nitric, hydrochloric, hydrobromic, hydroiodic. Notice that all of the halogens except hydrogen fluoride are strong because fluoride is so tiny and has such a big electronegativity that it won't let that H plus get pulled away. So the H plus is very strongly held, so it's a weak base, or I'm sorry, weak acid, because it will not lose its H pluses 100%. And then you've got sulfuric and perchloric acid. Strong bases are going to be the alkali metal hydroxides. So notice that they're all hydroxides. None of them are like ammonia that reacts with water to form OH. They're all ones that actually have OH already present. So they're metal hydroxides. So all the alkali metals, heavy alkaline earth metals, so the ones at the bottom of the periodic table, and then oxides of some metals are also going to be strong bases. They're going to react 100% to give you OH minus ions. So this is going to be the hardest one to remember. These guys you should remember pretty easily. But like I said, you need to know these. So in terms of dissociation, because acids are molecular, they are not ionic, they are molecular. The H is held with a covalent bond to one of the O's. They dissociate. And so because each H is held reasonably strongly, they lose hydrogens one at a time. So notice that nitric acid only has one hydrogen. It's going to dissociate to give you H plus and NO3 minus. Acids, sulfuric acid has two H's. Only the first one is strong. It loses that first one 100%, and you wind up with this hydrogen sulfate ion. So you got to be careful. Acids lose their hydrogens one at a time because they are molecular. So even the strong acid, H2SO4, only loses its first hydrogen 100%. Bases lose their hydrogens or their hydroxides 100% as well. Notice that you wind up with a mole ratio that is not always 1-to-1 like you have up here in acids. In acids, they're always 1-to-1. One H plus is coming off, and what you're left with is whatever the rest of the formula is. Bases, if they're strong, they're going to lose their OHs completely. And so take note of what's going to happen here. Sodium hydroxide only has one OH, so you get a 1:1:1 ratio. Calcium hydroxide, however, has two OHs, so you're going to get a 1:1:2 relationship. And then the oxides that you need to know, so sodium oxide is Na2O. It's going to react with water to give you two OHs. So this O is going to interact with the water and give you two OHs, and then we have the two sodiums there. Okay, weak acids and bases are going to dissociate much less than 100%. So they establish equilibrium. Therefore, there is an equilibrium constant, a Ka or a Kb. You can write an equilibrium expression for them. To get the concentrations of the acids or bases, you can't do just a simple mole problem. You have to solve an equilibrium expression in order to figure out what the H plus or the OH minus concentration is. So, for example, acetic acid, you put it in water and what happens? Some of this H comes off. So the reason why this H can come off is because this oxygen is going to be pulling the electron density towards it. So it's not really this O that's important, or else alcohols would be acidic. It's this O that's important that makes this hydrogen easy to come off. So carboxylic acids can become acids in water because all of the electron density is going to be pulled towards that oxygen away from this hydrogen, and so we can lose that hydrogen. So you're going to get H3O plus, and you're going to get acetate ion. So to figure out how much hydronium ion you're going to get, you have to set up an equilibrium expression. You've got the two ions in the numerator, and you've got the whole molecule in the denominator. Remember, we don't have to worry about water because it is a liquid. Ionization constants for acids and bases, you've got one of the appendices on the website has this. Your textbook probably has a pretty good version of this. You can see that perchloric acid, this is one of the very simplified tables that I showed you in the first unit, or the first set of videos, but now we've got Kas and Kbs here. So if you have a strong acid, okay, it's got a large Ka, so large that it's much, much larger than 1. Its base is going to be, its conjugate base is going to be very small, so weak that it's irrelevant. Once you get to something that is weak and it has a Ka, notice that its respective conjugate also has a Kb. That's going to come into play in a lot of ways in this unit. One thing I want you to take notice of, the Ka of the acid times the Kb of the conjugate is going to give you 1 times 10 to the negative 14. So there's something else to remember, especially when we do titrations. So as the Ka gets smaller and smaller, that means there's less and less dissociation going on. The Kb is actually getting bigger and bigger because it's willing to take in that H plus very strongly. So like I said, we can establish an equilibrium reaction. We can write an equilibrium expression for anything that is weak. And so you've got Ka expressions with the ions on top, the acid concentration on bottom, Kb's with the base on top, the ions on top and the base on the bottom. And so remember, if we translate this all into pH, as you increase the acid strength, Ka gets bigger, the H3O plus gets bigger. What happens to the pH? It's going down. Kb strength or pH is going to increase, but the H3O plus concentration is going to decrease. We have more OH minus around. So just remember that you've got a lot of inverse relationships that you've got to keep straight. So pick a couple that you know solidly, and then the rest kind of you can figure out from there. So let's take a look at equilibrium that involves weak acids and bases. So in this first example, we've got a concentration of acetic acid. HOAC is kind of the abbreviated version of acetic acid. I'm not sure why the O is in there. But HOAC is kind of an abbreviation for acetic acid. So we want to calculate the equilibrium concentrations of all three of these guys, given that, and the pH, given that the Ka is 1.8 times 10 to the negative fifth. So we are going to solve an ice chart. So initial concentrations are 1, 0, 0. What's going to happen? A certain amount of this is going to ionize, and then we're going to get an equal amount of those ions increasing in solution. So the change is all X. That's what's nice about acids and bases, or acids at least. The change is all X. So at equilibrium, what do we have? 1.0 minus X, X, and X. And so we are going to move on then to step 2. These things are going to go into the equilibrium expression. You've got Ka is equal to x squared divided by 1 minus x. This is a quadratic, so you got to solve using the quadratic formula. But remember that the nice thing is you can make an approximation that if x is very small, which it's probably going to be since the Ka is 1.8 times 10 to the negative fifth, if x is smaller than 4 or 5% dissociation, you can ignore this minus x, and then solving this problem is a little bit easier. Again, for you guys with the fancy calculators that let you solve, this doesn't really become an issue. You can keep this equation as is and solve for x that way. So then step 3, you're going to solve the Ka expression. And in this case, I assumed that x was really small, so I got rid of it. Again, the number you get is probably going to be slightly different if you keep the minus x in there and do the solve function. And once you have this, then we've got a way of showing what the percent dissociation is. We've got moles of the ion, which is 0.0042, divided by the whole molecule. So we wind up with percent dissociation of 0.45. That's less than 5, much less than 5%. So we are safe in taking that minus x away. So the number that you got by solving this without simplifying it and using your solve function should have given you pretty much the same value. Okay, I think we're going to we can do one more. I guess I got a couple minutes. Oh, we haven't actually finished this one yet. I forgot. We need to solve the other concentrations in pH, so it's good I didn't stop. So the concentration of acetic acid is 1.0 minus the 0.0045. Sorry, that's my dog. X was H3O plus, and the ion concentration, 4.2 times 10 to the negative third. And so then we're going to use this to get our pH because we got the H plus. We're going to do the negative log of the H plus, which gives us a pH of 2.37, sorry. Okay, so now I think we're going to pause this and do this next one on the part 2.